Thank you.
Okay, good afternoon, everyone. I'm Mingkun from Ocean University of China. On behalf of the cloud task team, I will now report on the progress we have made in cloud detection over the past year. This year, our team has made progress in three main areas. Firstly, Steiner validated the PPS cloud products. And I applied the Bayesian algorithm to cloud detection for high resolution infrared radiometers. Uh, the third one, Owen updated the Bayesian cloud detection algorithm in the CCI project and applied it to the Hamavari 8 and 9 satellites. Next, I will provide a detailed report on the results of the first two parts of our work. Firstly, I will introduce the work on the validation of PPS cloud products provided by Steiner. The PPS project has developed a polar ice temperature product based on SLSTR observations. Cloud detection is a crucial step for retrieving ice temperature products, and nighttime cloud detection often poses challenges. Therefore, this work validated the newly developed cloud mask products. The cloud mask from PPS includes cloud-free, cloud-filled, cloud-contaminated, and ice-snow-covered. The cloud mask products also comes with a cloud mask probability which is independent of the cloud mask. The combination of CMA extent and the CMA probe considers a pixel to be cloudy. This work used Kyler radar data for PPS cloud validation. The Kyler produces soundings based on laser pulses with 300-meter spacing. Therefore, the 1 kilometer products are derived from averaging 3 laser pulses. The time window for matching Corlett and HRSST data was chosen to be 3 minutes, and the data matching region is between 67 degrees north and 81 degrees north. Besides, the generation matchups also used the sea ice concentration product to separate ice and water surface. The matchup dataset provides a qualitative set with n pairs of cloud mask and cloud cover truths taken from Corlett, and we divide these in 4 subsets A, B, C, and D. These 4 subsets are used to calculate the statistical scores as follows. The probability of detection and false alarm ratio scores are used to evaluate the cloud mask. The FAR clear is important for temperature retrieval. It means how often the cloud mask falsely classified cloudy pixels as cloud-free. The Haysen-Kuiper skill score is a skill score that uses all the elements. It has a range from -1 to 1, where 0 indicates no skill and 1 is the perfect score. The probability of detection POD and false alarm ratio FAR are fractions of correct and false. Here is the validation results. In this table, the validation scores over C for the combination of CMA and CMA probe are shown for day, night, and twilight. The nadir view results for SSTR-A and the SSTR-B shows that the performance is good over C at daytime with high hit rate, high POD, and low FAR for both cloud and clear. The validation scores for SSTR oblique view and the combination of oblique view and nadir view are also shown. The net oblique view has higher POD for clouds for both satellites, while the FAR for clear differs between the satellites. FAR clear is lower for SLSTRA oblique than nadir with a low POD clear as well. So there is a few false clear, but also clear classified as cloudy. For SSTRB, there is a high FAR clear for oblique at nighttime, which does not correspond with the results for SSTRA. The validation scores for cloud masking with CMA alone, CMA probe that is higher than 50% alone, and the combination of CMA and CMB probe is also shown. The three shows very similar hit rates, while the Bayer's POD and FAR scores differs a bit. The combination of CMA and the CMA probe improves the scores by detecting more clouds. This is the conclusion of this part. PPS cloud mask has been applied on SSTR-A and B data for RST retrieval. The validation scores are similar for PPS on SSTR as similar instruments such as VIRS and AVHRR. In polar conditions, PPS shows good performance during daytime. At nighttime, the scores are good over water, but around 35% false alarm ratio over ice. The combination of a threshold-based cloud mask and a Bayesian cloud probability is a good combination for applications which needs a cloud conservative mask. So if anyone has questions about this part, please contact with Steiner for details. The next part is about the cloud detection from high-resolution infrared radiometers. I applied the Bayesian cloud detection for the thermal infrared the thermal infrared radiometers on board the SDJ-SAT. The SDJ-SAT, known as the SDJ-SAT-1, is the first satellite developed specifically for the implementation of UN 2030 agenda for the sustainable development, which is launched successfully into orbit on November 5th, 2021. The SDJ-SAT-1 is equipped with 3 cancer payloads, including thermal infrared, low light level, and multispectral imagers, orbiting the Earth on an altitude of 500 kilometers and an inclination angle of 96.5 degrees. This is the technical specifications of SDJ-SAT-1 thermal infrared spectrometer. The swath width is 300 kilometers, and the TIS consists of 3 channels spanning 2.5 micrometer, 10.3 to 11.3 micrometer, and 11.5 to 12.5 micrometer, with a spatial resolution of 30 meters. This is a demo image of the SDJ-SAT-1 TIS 11 micrometer brightness temperature. We performed the cloud detection on the TIS on board the SDJ-SAT-1 satellite using a Bayesian algorithm. The observed brightness temperature vector includes the observed brightness temperatures of the 11 micrometer and the 12 micrometer channels of TIS. For the texture part, detection part, considering that the spatial resolution of TIS is only 30 meters, and the lookup table for texture detection is based on historical observation data from AVHR and ATSR. We selected a 9 by 9 pixel grid for the calculation of LSD. For the simulated brightness temperature, we used the 25 kilometer background field SST and the atmospheric profiles from ERA5 as inputs, and performed atmospheric radiative transfer simulations using Motion. This resulted in the simulated brightness temperatures for the 2 channels after interpolation and the background field SST. It can be observed that near the coastal areas, due to the errors in the ERA5 SST, some anomalies appear in the simulated brightness temperature. So this is the results. Here are the brightness temperatures of 11 micrometer channel before and after cloud detection. It is evident that in most cases, the cloud detection works well. However, there are some instances of missed detection at the edge of the scene and broken clouds. Here are another detection results. In this scene, the aesthetic fronts and the details features are very prominent. We aimed to evaluate the performance of the Bayesian algorithm in detecting areas with significant brightness temperature gradients at the fronts. And this is the magnified image. Overall, most of the fronts were preserved, but there are some cases with the over detection. This indicates that there are still areas needing improvement in the future work. Regarding the improvement of the Bayesian cloud detection algorithm for high-resolution sensors, I currently have the following ideas. First, the 25 kilometer resolution of the background field SST is too low compared with to the spatial resolution of high-resolution sensors. Therefore, we can consider selecting higher resolution SST products as the background fields, or improving the background field SST through super resolution techniques. Additionally, the lookup table required for texture detection in the Bayesian cloud detection algorithm may have issues when applied to finer spatial features. So this aspect needs further improvement. Finally, because high-resolution sensors generate larger volumes of observational data, we should choose a faster RTM for simulation calculations. Finally, I will report on the future work our team plans to undertake in the areas of cloud detection. Focus on the cloud detection at high latitudes and improve the ocean sea ice discrimination. A validation of cloud detection using the Earth-Care satellite that will be launched soon. Continue the cloud detection of high-resolution sensors. The coastal zone and the coral reef area cloud detection areas. Machine learning enhancements to physically based methods of detection. That's all. Thank you.
Thank you, Mingkun. Any questions now? Anything online? Okay. Should we proceed then on task team 2 on climatology and level 4 intercomparison report, and Chunxue will give the presentation? Yep. And Jorge.
Hello, everyone. I would like to present also our co-chair, Jorge. We have been leading on this task for 2 years already. So I would like to present Jorge first. I don't know if you want.
Thank you. I think just following up, one of the reasons we believe this particular task team also is very important is because of the future of all of the new SST data sets. Plus, obviously, I think also with the comparison with the emphasis on coast and high resolution, I think some of the results with respect to the gradient comparisons also are very interesting. And I think this is going to be extremely relevant also as we move forward also with other important regions like the Arctic. So thank you.
Sorry. Okay. So, okay, should we? Ah, okay, take it out. Okay, thank you. um, next slide. It's not working. You see, it's our task team members. We have a list of members. Definitely, we how can I say? We have also new member Alvin just joined us last I think few weeks ago. Definitely, if you're interested in this task team, please just let us know. We can put you inside of our task team. Definitely, if you are not interested anymore, you can also let us know. We can take you out from the task. Okay, so next slide, please. Yeah, it's not working. The first task is working on the intercomparison of level 4 products on the climatology. We have accomplished a few years ago, so this already done. If you're interested in the paper, we already have the paper published in Journal of Climate. The second task is also the level 4 products. It's been on the compared to the in situ data. It's already completed 2 years ago, 3 years ago actually. Currently, there's a new intercomparison publications out. You can see it's highlighted in green. You can also have a look. I think it's a new work. They have defined the new improved climatology for the user. If you want to use the climatology of SST, I think this is the good reference paper. You can have a look. I will try it if it's working. No, it's going. Oh, okay. Now I see. Yeah, now it's working. Okay, this is the. I think I remember. Yeah, it's weird. It should be this one. Okay, then we have, now we start to look at the gradients. We have different types of tasks, subtasks. With the first subtask is the SST, the validate of the level 2, level 3, and level 4 gradients. Sorry, I'm reading from the other one. With the Shipborne data, you will see we have already publications available. You can have a look. And the second one is to have the visualization. You will see also the work from Prash. You have a online, how to say, the online display of the SSD fronts. And the third one is the calculate SSD gradients and intent compare. I think this is also part of the work of Daniel and also Jorge. We also have the, I think I will go quickly to the next one. I will just give you some specific. So this is the work, mainly worked by Jorge here, that they have compared the SSD gradient data with the Shipborne observations. You see at different regions, for example, the north of California areas. I think you also have a paper on the Arctic regions with the Shipborne data. So if you're interested in this work, please, you can talk to Jorge or you can check the publications they already have. The second one is what I was mentioning, the online visualization of the SSD gradients, but not only the gradients, but also the based on the SST and also ocean color and also salinity. In the last meeting, we have been thinking maybe we can also do the marine heat wave monitoring, because I think in the last few years, I would say, during the GRIST meeting, I think we also have sessions on the marine heat waves. Maybe we think it's a good moment already. We already understand the marine heat, not understand, I cannot say this big words, but I think we can do already the monitoring of the marine heat waves. I think Pallavi mentioned they already have one system, I think online system to see the marine heat waves. So that's why with Prash, we're thinking to have the detection directly here, so users we can have a look at the marine heat waves, evolution. Definitely, if you're interested in, you can talk to Prash as well. Okay, this is the also the I think this is the one with the with Daniel. Daniel is also here, and he has we have worked on actually compare the with mainly the Harmony data. I think the mission of Harmony satellite use different way of the SSD gradient calculations. Maybe Dina chair. Maybe I take. Okay, so this is already finished as well. So next one is the, you see here's the calculation of the gradients based on the, I think, I don't know if you have a paper on this one. Oh, sorry, we have the paper on this one. Sorry, the presentation will be on the CNR data set. But it definitely, if you interested in this paper, we can please talk to Daniel as well. So it's a little bit convenient on the change. Okay, this is another work. It's mainly done by David and also Nicole on the with echo stress, like what I mentioned by Jorge. Basically, the echo stress data is should be a land, right? If I'm not wrong, it's a land satellite, but they also cover the coast areas. I think also mentioned by Andre before on the Trisna data set is also the same concept. It's the land satellite, but they will cover the coast SST. So basically, they have compared the echo stress data with echo stress derived data SST with the Cedron data. I think it's also public. I think it's still public. I couldn't remember it's published or not. But yeah, not yet. And please, if you're interested in this work, David is here also in the audience, and you can have a look with talk with David. Okay, it's a little bit. Yeah. This is another result as well. The echo pixel with the Cedron measurement. I think this is also yeah. Okay, this is the another one is this we use a satellite use salinity data as independent to compare the SST gradient. It's also because usually we do either with Cedron data, but also this is another way. Basically, use other variables to see the SST gradient. It's also finished by Jorge. We can have a look at also the paper as well. Okay, next one is the work of is part of the European Space Agency project. The World Circulation project is mainly by is working by Daniel. I think you will give the presentation on this work. So I think will be tomorrow the Thursday. So Thursday So I'm not going to give any details on this one. So you can talk to also Daniel after the presentation. Okay, so this is also more details on the Mittaz presentation as well. He also is working on the SST gradient, but within the Mediterranean SST. Sorry, I'm a little bit difficult to read. It's small, it's too big. Okay. Okay, so next one is also the one of the Mattia. I think Mattia was going to have a poster as well on this topic. So the details, please talk to Mattia, is also in the audience. This is the one I'm more familiar with because with Daniela we have been talking about the SST gradient, but it's not only the one we saw from the visualization of Prash, because we want to see long-term changes. Basically, it's in the last more than 20 years to understand the SST gradient in different areas and internal variability. Since the last meeting, we have done a little bit of work. I think currently also working with Salvatore, we have been working on the how to say compare with the even reanalysis data set. Focus on we have choose the region on the west coast. The west boundary areas. We have also the time series of the gradient. That's what we want to focus on. So not only the very recent how to say the change of SST gradient, but more on the how to say the long-term variability, because we believe that the change of SST gradient also close to the how to say they're correlated with ocean dynamics. That's the idea why we want to focus on this area. But not only, I think Jorge, you are also working on the SST gradient in different areas, but in the locally in areas, yes. In the Barents, exactly. So we will, I think maybe we can work on this.
I have a poster.
Oh, the poster. Okay, Jorge also has a poster on this one, so we can, if you have any, definitely if you're, in the last intercomparison, we have contacted different agencies for the SST, but definitely for our particular task, we would like to have a SST a little bit longer period. For example, if it's 10 years or 20 years, it will be better. Definitely, if you're interested in being included in intercomparison, please talk to us. I think we will happy to have all the data producers inside of the intercomparison. Okay, so we have we have a potential. Actually, it's not even potential now because Prash is already working on. Because we have been talking about SST gradient, but definitely ocean color is also one of the independent data set. We can also see derive the gradient. So that's also the Prash and also Indian colleagues. They have been working on the also Mauron, also they work on on this task. Definitely, I think it's also our interest. I mean, it's interesting to combine the physical properties of the ocean and with the biochemical, which is ocean color, together to understand the front. Basically, it's more on the ocean fronts, let's say, on the definition. So I think this is the still ongoing, very preliminary, because in the last meeting, I think last year's meeting, we have been thinking the potential one, but now we already have some result on this task. I think that's what we have. Oh, sorry. We also have the other one. You can see already we have different. We already have. I couldn't remember in the visualization you already have. Oh no, it's just a new. Okay, this is a separate work. Okay, I think that's what we have. No, sorry, it's another one. It's the, sorry, I think you will talk to Prash on this topic then. Okay. Okay, I see. So basically, I'll repeat what Prash just mentioned. We want to see which level 4 data we can use to do this work, and data fusion is one tools to understand the data set. Okay, I think that's the end. So I just want to mention that I will, because my personal, I have too many commitments from work, so I will give my role to Danielle and Channy, and definitely with the Jorge, they will lead the task. Because with Jorge, we think that Danielle is really a good candidate to lead the task continuum, because he's very active and also has expertise on this ISST. So if you are really interested in this task, please talk to Jorge and Danielle on the to join the team.
No, I just want to take the opportunity to thank Junyi. Thank you. And just one quick thing, why I think, again, this is so important after being 25 years now that we celebrate GRIST, being at the PODAC. One of the questions hasn't changed in those 25 years. What SST data set do I use? And we still get that question, and I think this is one reason why these intercomparisons are so important for that and the documentation. Thank you.
Thank you very much, Jorge. Thank you very much. The other one, how to say, we are very, I would say we are very active in a task team. Usually we meet at least 1 month or maximum 2 months per, how to say, every 2 months at least, we meet together. So I think please join us in the task team. Thank you very much again. If you have any questions, definitely. Okay, please.
If I don't miss anything, so my question is, because the SST gradient is critically dependent on the resolution, spatial resolution, because different SST products has the different resolutions. So how do we deal with this situation? Do you have kind of saying we have to have calculated the SST gradient in a 1/4 degree resolution, both for different SST products as well as the in situ observations, or what are you going to deal with?
Well, that's a very good question. We have been discussing actually in the beginning already, because some data really have the high resolution, but the first step we want to do to interpolate. I think currently we will interpolate into 1/4 degree. Definitely, it will how to say, eliminate some signals, high resolution signals. But since we want to focus on the variability of the longer variability of the gradient, so that's the point we want to start.
Yeah. So my suggestion is maybe you have to use a 1/4 degree resolution, include both high and low resolution SST products or something.
I'm sorry?
Maybe you have to use a quarter-degree resolution for all these SCT.
Yeah, sure. That's exactly. That's also, even the first time we did the intercomparison of climatology, we exclude one data has 2 degrees because we don't want to downscale so much of the data set. That's why the minimum has to be 1/4 degree for the intercomparison. Yeah. Okay. Any questions? Thank you. Thank you very much.
Thanks both. And now moving forward with task team 3 on high-resolution SST drifters for satellite SST validation with Gary. Welcome.
Okay, good afternoon, everybody. I'm Gary Corlett. I'm a remote sensing scientist now at EUMETSAT. I've been chairing the HRSST task team for a few years now because I've had a very strong interest in comparing satellite data to in situ data ever since I've been working in this field now, which is unfortunately now 20 years. It's quite a long time. So not quite 25 of GRIST, but a very long time. Before I start, I thought it'd be useful to just revisit where we got to. And I think we must never forget the importance of in situ data for what we do. It's absolutely critical. And in particular drifters, because of their coverage, these are really a workhorse in everything we do. Without drifters, I don't think we'd have such a successful project. Many of you know most of the drifters come from NOAA funding. They're funded through the Global Drifter Program, and all drifter deployments themselves are coordinated by the JCOM Data Buoy Cooperation Panel. And when we first started to look in detail at the accuracy of the drifters, it was thought at the time that they should be giving around about 1/10 of a degree, and many papers, including those led by many of you in the audience, showed that actually it's probably closer to 0.2. So back in 2010, Chris Merchant and myself headed to meet David Meldrum, who was the chair of the DBCP at the time, to see what we might be able to do about this. And so actually we developed then, now, yes, back in from original concept in 2010, the idea of this pilot project. So we would try and then refine or come up with some specifications to improve the quality of the drifters. So we as GRIST came up with some requirements, and these were endorsed back in 2013. And really they sort of can be grouped into 2. I mean, there are a few others on there, but the first thing was to improve the positional reporting. Historically, drifters were only reported to 1/10 of a degree, and particularly new drifters, those using Iridium communications, would now be able to give us a better measurement. And so we had the idea of HRSST1 drifters. So these were the first drifters that came through from this project, where the calibration was still to be determined, but now we were a bit more certain as to their location. And then the second stage, of course, was at the time we set an accuracy of less than 0.05. In those days, we used to, of course, we didn't know what uncertainty meant. Sorry, John. And different things. And so we refined this now to a total uncertainty of the drifter measurement to be less than 50 millikelvin. And we were very pleased to see, so back in 2019, for those of you who were at the GRIST meeting at Esrin, Lucas Centurioni from Scripps, who was leading the DBCP, actually showed some information at the time to show that actually since then, most drifters deployed are meeting the HRSST2 requirements. So really the objective of this task team is a fairly open one, really, to coordinate the HRSST activities and really to look at the HRSST2 drifters and see whether we can see any benefit. Have we seen improvements in the in situ network according to our things? And just the first point to stress here, I'm not talking fiducial reference measurements. You will hear about the trusted project and fiducial reference measurements later. This is an extension of the HRSST activity, the overall aim was to just improve the quality of the entire drifter network, and this was HRSST 2. So the task team, as you can see, so there's a lot of names familiar to you there from the GRIS community, but as you'll also see, there may be some names that are not too familiar to you because it is very much coordinated with the in situ community, the DBCP, and especially those involved in the NOAA Global Drifter Programme at Scripps. If you wish to join, obviously feel free to drop me an email. And I think there are probably a few names on there that, yes, I think according to the last one, maybe should not be on there anymore. So the current work plan really was to do a performance assessment. So can we categorically show the HRSST2 drifters are better? And so to be able to do this, we have to be able to identify them from the metadata provided. And this has taken quite a bit of time to ensure. So one of the things that GRIS stressed very much from the beginning was the importance of good metadata and metadata management. And not all communities have had this. And in fact, this is one thing where the in situ community certainly has been improving on. So we've been working with them so that we've got some clearly simple metadata that we can use to be able to identify an HRSST2 drifter. And then the second point there, and again, I have to stress this. So at the moment, the best definition we can come up with is if a drifter is using iridium, but unfortunately not those from the manufacturer DBI, then they can be classed as an HRSST2 drifter. So we can use the metadata available to identify this. At the moment, there's not a simple program or a simple type or a simple tag because it needs a lot of other information to go through it. But I must stress, this doesn't mean there's anything to be concerned about for the DBI drifters. This is just because their calibration has not been confirmed with a laboratory certificate. That's the only reason we don't include them at the moment. So it doesn't mean there's anything wrong with the data. It just means we cannot say, yes, that is an HRSST2 drifter because it meets the iridium reporting requirements and it also has laboratory calibration that confirms its accuracy to be less than 50 millikelvin. And we continue to work on the minimum metadata specification, and I'll show you that on one slide. So at the moment, one of the methods I'm using to evaluate them is to use the Copernicus SLSTR dual view 3-channel retrieval. So this is the nighttime using 3.7, 11 and 12 micron. This is our best quality data we can provide. And I should have emphasized now, I'm turning this around. I'm now using SLSTR to tell us the quality of the in situ data, not vice versa. So I use a 5x5 extract around the buoy location. And this is really to try and reduce any sort of residual cloud contamination errors. This is fairly common within the community. I use a time window within plus or minus 2 hours. The buoy SST, we assume, is at a depth of 20 centimeters. This is the mean average depth of a drifter for example, if you are holding it. Whether it's like the same depth as the water as it's moving is questionable, but given that we only really care about strong diurnal variability in very stable conditions, the 20 centimeter is a reasonable approximation. And so to adjust that to the skin retrieval of the satellite, so SLSTR is an infrared retrieval, an infrared sensor, and so it's sensitive to the skin SST, so we retrieve skin SST and then adjust. So again, because I'm doing this backwards, what I'm doing is then adjusting using the same models. So in this case, a UK Met Office implementation of the Ferrell and Cantor and Clayson models to be able to take the in situ measurement, adjust both its depth and its time so it's more comparable to the satellite. And then because, again, I want to make sure that I'm removing any issues with the satellite data, I only use all 25 pixels when they're flagged as clear. I should add that this may mean that some large-scale cloud contamination gets through. There are, obviously, we know we can have issues with infrared sensors when the cloud is very close to the temperature of the surface, particularly at night time, and it makes it quite difficult to detect. So they may have sneaked through. We don't use anything within 10 kilometers from land. And then also, We look at the variability in the SST pixel, and at the moment, anything less than roughly about 400 millikelvin per kilometre is removed. And this again is just because we want to make the comparison fair between the satellite and the in situ data. So the original aim for the meeting and the bulk of the work was to take the data from JCOM-OPS. Unfortunately, when my time allowed me to work back on this project, the JCOM-OPS website has been down. We were hoping it was going to be back up for the meeting, but unfortunately it's not quite yet operational because we want to take the real-time metadata stream. This is the other thing we're testing, not just the quality control. We want to take the metadata stream. So at the moment, I'm still taking data from AOML in Miami. So we take two different files. We take their deployment log, and then we take something called DRAW, because this allows us to determine if the drogue is still on or off the drifter. And then from that, you can identify an overall QC flag, the manufacturer of the buoy type, drogue status, etc. So there are a lot of information you can gain. And the idea from the JCOM-OPS site is all of this information is then available and is through machine accessible APIs. So for example, I hope you can see the plots. So on the top plot is showing you now results from that subset of matchup data for Copernicus SLSTR-A. So on the left-hand side is a spatial map. In the middle is a Hofmüller diagram over time. And the bottom plot are the non-HRSST drifters. And at the moment, there's no drifter QC applied to this data whatsoever. And so you can get an idea, I hope you can read the numbers, of the number of matchups you get for the two different data sets, their coverage in time. You can see if there's no QC applied. Although most of the plot is generally grey, that means it's within 1/10 of a degree, which is probably what we think is the limit comparing a satellite to in situ measurement. You can still see there are some hotspots in the data, and these are much more noticeable in the bottom plot. So of course the question is this the satellite, the in situ, or both? And then on the right-hand side, there are different statistics. So there's a normal standard deviation, a robust standard deviation, and then also the result of a Gaussian fit. Because of course, when we calculate statistics, we are assuming they're Gaussian, and this might not be the case. And quite often with Earth observation distributions, the final distribution is not Gaussian. So very quickly, this is what you get with no QC. If I then apply QC, then you notice a few things straight away. The first thing is there's quite a change in the coverage now for the non-HRSST drifters. You also note there's still some hotspots in the data. So this is quite clearly issues, as I said before, where we still got probably some residual cloud gone through to the data, or maybe the QC is not working. But the biggest changes are over here. And that's to compare the number of matchups between the two slides. So in this one, we've still got over 51,000, and this is down to 5,000 on the previous one. So we've lost nearly 50% of our matchups for non-HRSST drifters using the QC, whereas for the HRSST drifters, we've lost about 100. So that clearly shows how good the HRSST drifters are, because extensive quality control is removing very few matchups. And in fact, you can see now the robust standard deviation. Now remember, this is for a matchup distribution. This is not for a perfect algorithm comparison. So for SLSTR D3 against all of the quality control drifters now, we're around about 0.18, 0.17. And if you saw the talk earlier, you can see that even the systematic part of the retrieval is contributing about 0.11. So if you consider we're comparing a satellite via a model to an in situ point measurement, quite clearly, not only are our assumptions correct, but the data quality is very good as well. So finally, just on the minimum data. So the ones that are coloured black, so these were the ones proposed by the DBCP, which we accepted many years ago. The ones in green were added at GRIST 2019. And then I think we probably should just add the one in red, that I think an overall quality flag is probably something that we overlooked, which would be useful to add to the data. I think it'll make it more usable for many other people who don't have the experience to go through all of the metadata. So that's where we are. So we need to finish this, but we need the JCOM up site to be up, because we have to be able to demonstrate this using the machine assessment. So we want to just, if there are any other changes or if there's any other metadata you think should be added for your work, please let us know now, because we need to finalize that list, because that's the list that we're going to hopefully have for every single drifter. And then we, of course, have to write up the work in a journal article. So moving forward, so I hope, because of the delay, we did hope to have completed this work by GRIS 25. So I think, unfortunately, the task team will need to continue for another year, particularly so we've got time to work on the journal article. And I think there's just a summary then of work we've done, which has mainly been presentations, because again, this has had a very strong interaction, and we're very grateful for the feedback as well with the in situ community. And I'll stop there. Thank you very much.
Thank you, Gary. Questions? Go ahead.
Hi, excuse me if I'm kind of not knowledgeable about this, but the DBI data that you say you're excluding a lot of, you're losing that. Is the information available? Could you reprocess the metadata and go back, or is that just not at all accessible?
No, it's not available, unfortunately, for we just don't know. I don't see any great deal. I haven't showed the results, but I have showed them in a previous GRIS meeting. I don't see any differences between most of the drifters and the DBI one. It's just I'm specifically tasked with assessing the HRSST2, but I don't think there's a problem with the DBI drifters. Far from it. I think they're very good. They should be used. Okay.
Okay, thanks, Gary. And now moving forward to task team 4 on shipborne radiometry with Fred coming up on stage.
Hello. So I'm Fred Wimmer from the University of Southampton, and it's about shipborne radiometry, the next task team. And there are some slides from partners. So we have a network of all the people producing radiometry data and of some users. There's a data format, there are EOIs, we haven't quite finished that, and best practice documents on the web page. Yes, so we have members. Quite a few of them are here and they're producing data. There's the web page there, shipsforSST.org. We have a data archive, thanks to Jeff at Ifremer, and we have a data format which is very similar to the GRIS data format. It's the level 2 radiometer format, so it has a few things in it which we need for our data. There's always the question, do we need updates to the fields? Talk to me if you think we need other things in there, what's important, what's too much, what's not enough. We do the coordination of activities, that's mainly me. Protocols and procedures that can be found on the web page. Data collection has been okay, but especially COVID was troublesome for us because we didn't have access to ships. We're reliant on people allowing us on the ships like crews and ferries. I was quite restricted. And also there's it's always a bit there. Some people in the group are directly funded and some people are not necessarily funded for this activity. And they use time and energy when possible, but that has come up that producing the files in the L2R format isn't as streamlined as we like to be, and it can be an issue, but we're working on that. And also the integration with Felix at times could be better, especially EUMETSAT Felix. They're working on it, thanks Igor and Gary, but it's not quite as streamlined as we want. That's the data we have in a global plot, so it's quite patchy, but it's much better than when I started. You see there are areas where we could do with more data, but yes, the instrumentation isn't that cheap, and we have a limited amount of, these are the data producers. So in blue is MERI data from the University of Miami. In green is sister data from the Rutherford Appleton Laboratory in the UK. Red one through the Atlantic and around the Bay of Biscay is the ISO data we have from the University of Southampton. That's my work mainly. The slightly lighter red is the data from ISO data from DMI in the north, and then the yellowish data around Australia is the data from CSRO, also ISO data. And now we come to some of our problems in the last 2 years. You can see 2023, quite reduced data. I mean, our bread and butter is the DMI data from Denmark to Iceland and our data from the University of Southampton, Bay of Biscay, but it's quite limited globally. And then there's one cruise from University of Miami, and sister data is on the Queen Mary 2, and she does the round the world cruise, so we have that in green. But this is where my point is, we have some issues with people providing the data because of funding issues. You can see sister, they reprocessed some data, so we have the North Atlantic cruises again, and I processed some of the MERI data to be in L2R, so we're filling in more and more. This is time consuming, and we haven't quite the resources to do this as quickly as we want, but we're working on it. And if you look at it in monthly plots over time, so that was 2020. You can see the impact of COVID there in the middle and dropping out some of the data. 2021, great, but we recovered. Mainly, as I said, ISO data in European waters. And then this is where we're recovering data now slowly. 2022, that's how we started on the left here a year ago. And now we have at least some of the Queen Mary 2 data back in the archive. And 2023, this is the MERI data I recently started processing, so we're gaining that back as well. So the data is processed for MERI data, but it's not in the L2R format we need for the archive. And we're working on getting that into the right format and into the archive. Apart from that, we've also been working on something I called newish. I presented it last year, and we have made some progress on that. It's a new radiometric instrument. It's called the Astron. You can read all this about here. And basically it came across as a UK government fund. The UK partners in this network got access to, and we're working on that. So it's mainly the Rutherford Appleton Laboratory and us at the University of Southampton. We're working on that. There's the list of partners. Leicester University is the land partner, and MPL for calibration. But it's a purely UK project at the moment, but we hope to expand it once we have the instruments ready. And the reason why we started a new radiometer is because the existing ones are getting quite old. I know the MERI has a new generation, but ISO and sister, they are 20-odd years old, the design, and it will be an evolution of existing designs, and is also specifically designed for ice and land surface temperature, which the previous ones weren't, because they're mainly for sea surface temperature measurements. You can read the requirements. It's box standard stuff. And yes, it'll be self-calibrating like the previous one, multi-view, autonomous in operation and data transfer. And the last point is mainly for land deployments. It has to be reasonably light and transportable and very easy under power consumption as well. There's a channel list. So this is a difference. MERI is a Fourier transform radiometer, so you can do all channels, but sister and ISO, which are order of magnitude cheaper than a MERI, are filter radiometers, and so far they only had one filter, but this one will have in its early incarnation these six filters in it, but it can have up to 8, and the user can make different ones, but that is one of the most expensive part of this instrument, is getting the filters done. So you can change them, but it's not super simple. And the first 3 channels are for the land surface temperature and emissivity calculation. Then you have the classic split window, and we added an air temperature, so you can do air temperature radiometrically on this instrument. And these are the filter bands plotted up. So you can see roughly that the land 3 ones at 8 and 9 micrometer are quite narrow. The split window ones at 10 and 11 are quite wide, and the air temperature band is somewhere in the middle on the wideness. Classic design is all modular, so you have a data bus in the middle of the instrument, and all the individual components talk to that data bus, so they're fairly easy to update and change if need be. And that's where the design is at the moment. And you can see, where's my the laser pointer? Oh, there. There's a parabolic mirror here. There's a detector here. There's filter wheel here. Chopper plates in between. Scan mirror. Black bodies for self-calibration. And then there's the door is still missing in this plot, but we're working on that. But this is the current design, and we're actually producing the parts so to get on with making the instrument. So this part here is the chopper cassette. This is the chopper here. This is the part where the motor runs in. This is the view aperture here, and that's the filter wheel with its Geneva mechanism. You can see the 8 positions there. When this design phase has more or less completed, we're doing some final touch-ups. The definite design review was in January. We've started to manufacture bits. Calibration will be end of the year at MPL, and deployments early next year of the final instrument. Slightly behind our original schedule, but that's normal with building stuff. The work plan for the next year for this task team is, fix and improve getting the data into the archive and the timeliness on the Felix matchup production. Ensure that the data is up to date in the archive. We're working on that as well, and publish validation results. I haven't shown here, through Felix, we do standard validation of SLSTR, and it's looking very good, but that relies on the timeliness of data on the archive. And there's a number of members on the team. If you want to join us, just talk to me. We can add you to the list. The delivery schedules are, we have published the intercomparison. That was last year, was an intercomparison to prove our traceability to SI, and has been published early this year, so people can read up on that. And we still have to do the publication of our validation results. And there's the web page, and we have a Twitter feed. That's that. Questions?
Thank you. Wait for it.
No questions?
Yeah. Andy?
Oh, no.
So you mentioned new technology and all that. What's the, is there any improvement or otherwise with respect to things like any delta T for the new radiometer? Because obviously you've got narrow channels and stuff like that, and you've got a chopper, and where's the trade-off, or is there no trade-off because of new technology?
There isn't that much new technology in it. It's just easier manufacturability and cheaper and more channels. But yes, it's the old trade-off. Narrow windows will give you less throughput to the detector on the narrow channels.
So are you staring for longer, or are you, I mean, where is it literally one for what? So what compromise have you decided to make then?
Sorry?
Or is it just a matter of how you operate the radiometer?
It's a matter of how you operate the radiometer, and on those land channels we haven't, I mean, Peter has measured in with Mary on 8 micrometer, but we haven't with the filter radiometer, so it will be, if we don't get the throughput longer staying there longer, average it.
Right, so because it's configurable, you can do what you want.
Yes.
Okay, right.
But it will be a learning curve on that respect.
Thank you. Erika?
It's just because I saw your last slide and you had Slack under the last one.
Yeah.
But there we have a channel for you. Has been set up, so I can send you the link again to this and invite.
Yes, please. Yes.
Yeah, and also to all the other task teams, if you would like to have a
we have a Slack channel set up for all the task teams, so we can reactivate these, and I can send them out to everyone if that's the way that you would like to communicate with each other and stay in contact. So.
Thank you. Yes.
And now on task team 5, on the matchup database standards, Jeff?
Yeah, okay. So yes, I will present the status of this task team. So the slides have been prepared by the chair of this task team, so Igor. And the main goal of this task team is to evaluate and to collect and evaluate the different practices to generate matchup databases for SST. And the way these matchups are used to provide validation metrics and diagnostics. So this is the current list of members. So like for every other task team, people are welcome to join or leave. So in the last few months, since the last GRIST meetings, there were not many exchanges within this team, so people may feel like nothing happened, but in fact, as I will show, we prepared some required steps to move forward. So you can expect for the people who are here or the people who want to join, you can expect now in the next in the coming year, so more frequent exchange and video conference to work on the tasks that are in front of us. So in fact, this is the list of tasks for that compose the work plan for this task team. So the first task, which is well advanced and is in fact an ongoing task for the whole time frame of the whole life of this task team, is to collect journal papers or technical documents that explains criteria used to build matchup databases, the tools that are used for that, and the metrics that are derived from these matchups in SST analysis. In the second step, we have a task. We have a more detailed assessment and of the different MDB tools that are available at different places by the SST producers. So we try to do like a comparison matrix of all these MDB tools with their respective functionalities. And this task is in fact almost completed because we have a fairly comprehensive list of already of tools and practices with respect to the matchup production. So we are moving now to the third task, which is more about the metrics and protocols that are used to validate SST from matchups. And so the different aspects to look in this task is to identify first the list of validation and reference datasets, like in situ datasets that should be used for the production of the matchups and the comparison with satellite SST. Then to identify the different metrics and protocols that may be used for the SST validation and analysis, and kind of classifying these different metrics with respect to the type of satellite or in situ measurement we are dealing with. And the plan then is to have in task 4 a round-robin validation exercise, which is mostly based on a common way of generating matchups to look at the different ways of using these matchups to produce these validation metrics and kind of understand the differences and provide some recommendations and way forward on how we could harmonize this. Which eventually would lead in task 5 to the writing of a white paper and some online recommendation to GRIST SST producers. So the plan for the coming year and up to the next GRIS meeting is to progress on the preparation of the MDB production cloud framework. So this is, I will talk about in a minute. So the idea is to work on a platform to install a MDB production system. So this is Felix, and to try it on different sample data sets in order to provide, to produce matchups in the same way for any of these sample data sets. And then based on this common matchup production using the same tool, the same method, we can work on the evaluation of the different assessment metrics, which will be the next step immediately after this, and go into this round-robin validation exercise where we will intercompare this based on different kinds of data sets, so different processing levels from L2P to level 3 and level 4, infrared and microwave sensors, so high resolution, mid, low resolution, polar orbiting or just stationary satellites, and also different type of in situ reference data. So we don't expect to finish this round robin by next GRIS meeting. So that will likely continue and be completed in the next year after the meeting in Copenhagen, and hopefully leading to this white paper and to complete the work of this task team. So this is the framework that Igor has been working on to do this assessment of the metrics and this round robin exercise. So in fact, this is based on the WKO Science Cloud funded by Europe. So we have allocated some virtual machines on this cloud together with some storage. And this is where we produce the matchups for different data sets that we collect either from this platform because it already hosts a lot of data sets from EUMETSAT, from Siemens and so on, but we also collect other sample data sets from PODAC, for instance, or any other store that would include the round robin exercise. Then we produce with Felix in the same manner a set of matchups, so using the same reference data and hopefully over the same time frame. And all these different MDBs are made available for analysis and round robin through the local the bucket storage available on WKO, and can be used, for instance, through Jupyter notebooks. So it's even possible to use by signing in on WKO, you can have free accounts that give you even enough resources to work on through Jupyter on this MDB. So up to today, we have tested so the generation of this test data set for a different source of satellite SST data. So making sure that we were able to produce these matchups in a consistent manner. So we have used drifters and Argo floats as in situ measurement. We have tested this matchup production over a single day for now for different level 2 products, so SLSTR, VIRS, and OCSAF, HRR. On microwave with MSR2, we have tested on Ostia level 4, but also on some Siemens level 3S product. So everything now is in place to produce this test data set. So we need to agree probably in the coming exchanges within the team on the exact list of data sets that we will include in this round robin. And then we will generate a full matchup data set. So the extent of this data set is still also to be defined, should be 1 month, 6 months, 1 year. This has to be discussed, but at least the core technical issues are now solved, and we can really go to the more science part of this work. And we also we are working on providing some tutorial notebooks on explaining how the matchup database are built, what is the content and structure of these different data sets, and how you extract the information from this. So we will provide different notebooks like this to for users to fairly understand what is available and how you can use it to start calculating the assessment metrics. Okay, so regarding this task 3 on metrics and protocol, so as I said, we will have to discuss within the team and with the people who want to join the team in the coming months about exactly how we define the template for this MDB analysis. So which data set we should select in this intercomparison exercise, how we should compare to in situ data. So one satellite to the closest in situ measurement, or should we include also neighboring in situ measurement in the comparison, the type of statistics that should be used, simple statistics or robust statistics. Should we compare only the closest pixel, or should we work also on the neighboring average pixel? So there are many different things to discuss and to assess to understand what we want to exhibit through these statistics, and also the type of diagnostic that we want to deliver. So, for instance, the dependence of the bias over different variables, such as the time difference, water vapor, the wind, latitude, and so on. And so decide also which diagnostic as a plot, histogram, uncertainty plot, and so on should be produced. So somehow this should lead also to revisit the status of this GRIS validation protocol document that was written at some point by Gary and is not really straightly available from a GRIS website. So this is an opportunity also to rework this. Regarding the round robin activity, so we'll focus on comparing so the different MDBs that we have generated. So once again, we don't compare MDB production tools here. We used a single tool to generate all the matchup in the consistent manner, whatever the satellite source. And the computation is based on this Copernicus Wakeo platform. So as I mentioned before, so we need to now to better define the test data sets that we will use and on how long we should produce matchups and so on. So yes, so the plan for the upcoming activities is to complete the MDB analysis templates that describes the different metrics that we can produce from matchups. Work on these round robin activities that will not be completed by next GRIS meeting probably, but we will like to start on this on the second half of this year once we have completely solved the platform issues and the generation of the test data sets. And so, yeah, as I said, so now with all these resources and test data set, we can really start working on the science part and exchange more regularly within the team. So like every 2 months or something like this. So these are the deliveries that have been produced so far. So as I mentioned before, the first document is the collection of tools and so on that that have been collected in the first task. So the deployment of the cloud resources have been started, and we have already some test data sets that now we need to extend and complete and start working on, as I said before, on the round robin and eventually on the production of recommendation and the white paper. So the main reason, since there was not much exchange with the team, was really because of these technical steps that we had to lay out before to start really the interesting work. So there was a Felix matchup production system itself, and the allocation and preparation of these cloud resources so that we can all work together on the same data sets and same resources. So this is it. This is the plan for this year and the next year. Thank you.
Thanks, Jeff. Any questions? Yes, please go ahead. Will you please go to the microphone? Thank you.
Before you do this match-up SST between in situ and satellite observation, so my question is, what kind of quality control you have to be applied before looking for match-ups? Because some satellite or even in situ observation may be not as good, or there's some, anyway, there's bias and kind of random errors we need to be filtered out before we do the matchup, right?
No, for the production of the matchups, we don't do any quality control, but we do put in the matchups all the quality information from the satellite data and also the quality information that may be provided together with in situ data. So in fact, it's part, I think, of the work on this validation metrics and so on, also to define what we should do with this quality information, both from satellite and in situ. How should it be taken into account and so on. But we have not done anything specific on this for the matchup production itself.
Yeah.
Anything online? Okay, thank you so much. And moving forward to the last task team 6 on climate data assessment framework, John. Thank you.
Okay, well, fortunately for everyone, this is actually going to be hopefully quite quick. I do apologize for not having put it in the right template, which I noticed everyone else was doing, but I forgot and it was done late. And anyway, I apologize. So this is talk about the CDAF task team, climate data assessment framework. You can see the members here. And for those of you who don't know, the climate data assessment framework basically is trying to set up a framework for a climate data record. So ideally, a user could compare different climate data records. There is no intent within this framework of ranking climate data records. It's just providing information that users can use to make their own mind up, basically. So it supports users. Light. What's the light? Oh, there. Oops. Oh, I don't know. It's used to support users of sea surface temperature data sets to understand the suitability. It will provide, when we get there, authoritative comparable information so people can make their own mind up. It's been in existence for several years, but for some reason, and I don't know why, our team has been picked to people who are very, very busy people doing lots of other things. And so progress has been relatively slow. It's not that we haven't made any progress at all, but it's that it's been slow. Moving on, in terms of the CDAF, it's split into these different compartments, if you like. There's basic screening, there's generate measurement information, there's the idea, once you've generated all of the statistics, it will be reviewed by selected reviewers, basically to make sure that the system has worked sensibly. And then it will be published, and then people can then make their own decisions about what particular CDR they think is good for their application. The metrics were defined in the original documentation, so they're all quantitative. So there are looking at systematic differences against, for example, drifting buoys in situ measurements, systematic differences against Argo, which is more accurate, but you have less observations. The data will be binned spatially, so you'll get some estimate of regional variability on sensible spatial scales. Look at non-systematic effects, and then have some sort of metric for stability. The plan at the moment is to use simplified methods from a paper that Chris wrote about a decade ago. And where possible to include SST sensitivity metrics, although I would say that the ability to provide that information is up to, in a sense, the data provider, because it has to be done well, basically you need radiative transfer modeling to do it. And if that's not part of the process of deriving the CDR, then we won't have access to it. But where possible, we will provide that. And this is just a form. Again, this is taken from the original documentation. Our idea is to is electrify the word? I don't think that's the right word. How do you say it when you convert? Digitize, I suppose. Make a digital version of this so it can be put on a web page or whatever, rather than something having to fill this out by hand. And the idea is that the data providers themselves will be able to generate the statistics to go into this form. It's not that we'll have a centralized group of people who will do that for you. And so the workflow itself, and this is something that we have discussed this year. So this is where we've made some progress in that we have discussed some more aspects of the workflow. So you can see that this is using Felix. So we will be leveraging off what Jeff was just talking about. Essentially using the climate data set and the reference data through Felix to produce matchups. The MMD then goes into something that takes the matchup database and provides the diagnostic values, produce the diagnostic values, then go into some reporting that will then go finally into the output of the process. So each process in this can actually be deployed and used independently or linked together. And as I say, our initial idea is that at least the generation of the diagnostics should be able to be run by the climate data producer themselves. So in terms of the matchup database processing, so this will be based on Felix, the unique set of references from the situ data and using the Felix matchup system. Felix, as Jeff was saying, I think, it will be able to be used on the cloud where the satellite data are likely to be stored. I know that Ed was talking about the fact that, at least as far as NASA is concerned, everything will be on the cloud eventually. Jeff was talking about Wikio in terms of the European cloud. So certainly there will be certain data sets already that will be cloud available. Alternatively, it should be able to be installed on the CDR producers platform as cond packages. And they will then be able to run it themselves, pulling the matchup data from known reference sources. And then, of course, we will provide configurations for different forms of the data, of the GDS formats. And then there will be an output format which will be consistent output. So that's where you begin having the ability to compare different CDRs to each other. So in terms of the overall work plan, there's things like get the reference data, which, as I said, we'll be leveraging off the matchup task team. Produce the matchups, which will be Felix-based, which again is leveraging off the matchup task team, but there will be specific scripts to do with the CDAF process. As it says here, an initial test matchup dataset has been produced for us, but it's not yet been integrated into the generation of the diagnostic tools. As much as possible, we intend to use existing code. So, for example, we have rewritten code from Gary into Python to start doing this diagnostic generation. And our current set of metrics are deliberately simple to make sure that we can actually get something working. And in terms of the output, Prosanjit has already started thinking of it. So this may sound like there's a lot of we've been thinking about it rather than doing. Some of this has been done. And this year we have spent some time thinking about it. So when people start getting a bit of their own time to be able to do things, we can start doing it the next year. So the plan is to start moving on. In terms of the web design from Prosanjit, this is just an example where we've actually just effectively got things like Python scripts, Python notebook down there, which we've already worked on, and then we will look into the rest of this design. Here is just from Rishi about the conversion that we've done from Gary's IDL code to Python. And so we have Python notebooks for some of this. Here's a direct comparison between IDL and Python. This was all done last year, not in the last year, but in the year up to the previous grist. Here's just examples of the sort of plots that we're generating, things about stability. So just to conclude, we haven't actually done much in the last year because everyone's been busy, but we've talked about what we need to do for the next year. Some of the code has already been converted. We already have an example MMD. So the interfaces need to be done. We need to start looking at some of the variation statistics, such as seasonality trends and regional, and set up the initial interface. So the intent basically is, in the next 12 months, we hope to definitely have done get all of the Python code we need to do the diagnostics. I think the idea is that we already have an MMD, but at least work will have progressed on providing scripts so that a user can generate their own MMD. Whether that will be finished or not in the next year, that will depend on, for example, Jeff's pressures. So yeah, we're still working on it. The reason why I was happy enough to stand up here and basically tell you since the last grist we haven't done very much is that, but we are still thinking about it. We are still willing to work on it, and we will get there eventually. So thank you.
Thanks, John. Any questions? Yep. Jorge, would you like a microphone, Eric? Yeah.
You can talk to me directly.
Thank you, Jonathan. Is there any, I'm sorry, is there a focus on specific grist data sets to start, for example, the matchup and, in this work? Are you focusing on certain, level 2, level 3, level 4?
Given it's what I know, we will almost certainly start with CCI. Because I have immediate access to A, the people, and B, the data, so we can start working on that. But I mean, when we get something that is able to be used, we will release it to the community and tell everyone, please use it. And we may even nag people, but we haven't, until we get something that's usable, we're not ready to start saying everyone use it, and we think that the Bureau should do it, and EUMETSAT should do it, and CCI should do it, and NOAA should do it, and start nagging people. But certainly, I think the first thing that we'll be testing on is probably going to be CCI, because that's what certainly I have the most experience of. In test mode, yeah, to make sure everything is running. Yeah.
Any other question for Andy?
No.
Yeah, okay. No, Andy.
Yeah.
Stretching also.
John said earlier that he wasn't prepared to ask a question to somebody else because he hadn't given it enough thought. And I said, that's never stopped me. And you're about to find out why. So you mentioned the sensitivity being up to the provider, and I absolutely understand in the first instance, it's definitely the easiest place to go. Is there any way that you could sort of reverse engineer it? I mean, the big problem really is trying to get hold of the coefficients that are applied for any particular observation. But you've got a lot of other supporting data there. You could run it through the CRTM and the channels, and
you could. It's not in the current plan because that's like, oh, that's quite a lot of work.
Yeah.
So that's why we said that we would leave it to those providers that can provide it. Whether they do or not, we may have to nag them about that and say, well, we know you can generate it even though you're not.
Yeah. I mean, the thing is, of course, is that it's like they might start doing it, but would they go back and all those sort of things? So I don't know.
Yes. I mean, to begin with, the idea was to keep this. The reason why I said that it's simple metrics is because it's to do with how much effort we have available to do stuff.
Right.
So in an ideal world, you would, of course, try to at least either get the producer or maybe even provide code to the producer that they could just, compared to their data, have a link in so that it runs the RTTOV or the CRTM or whatever and pulls the ERA5 from wherever and does it all for them, but they just have to run it.
Right.
That may be an option, I suppose, if it doesn't exist already. But that is not part of the current CDEF plan, in that we definitely don't have the manpower for that, because, I mean, I'm not sure about the other task teams, but certainly at the moment, no person in this task team has any money at all to do any of this. So this is all done on best efforts.
Yeah.
Well, what do you want me to say?
No, that's it. That's fine. So it's a nice idea if only there was funding and effort available.
And we all know that.
Yes.
Sob story.
Yes, we can. Fine.
Okay, then sit down, please. You're fine.
Maybe.
You can ask another question, Andy. I guess nobody else.
Okay, thank you.
Thank you. Thanks to everyone again for the presentations. And now we move to an 1-hour session on Q&A and discussions on the task team reporting. Is that right? Open. Any points to bring up? Any thoughts on any of the presentations? Anything to elaborate on? Anything online?
Yes, there is one hand up.
It's a question for John. Would you be able to read it, because I don't have the...
No, I think it's we can ask the person to speak up, to open the microphone.
Hi, John. Please turn on your camera and your microphone and then ask your question.
Oh, yeah. Oh, thank you. A quick comment on Gary Corlett's presentation. He mentioned about the ocean ops, the GCOM ops side was done, which was true starting from February, but they just tended bring it back on very, very recently, and gradually not every function are back yet, but it's starting getting back. You can check it out. That's another thing that the ocean ops was done because their funding level is not enough keep everything going. So they basically the goals community is selecting feedbacks from the community. So if we have feedbacks on the utilization of the ocean ops, you can get on their ocean ops website, provide feedback to them directly, and that will help them as well. That's basically my comments there.
Anything to say, Gary? Up to you.
Yeah, no, thanks for that, John. Yeah, we've been in touch with JCOM, so we're know the progress. But at the moment, the site is still not fully activated, and they've advised us not to use it until it's been through their verification process. So we're expecting in the next few weeks, hopefully, all of the verification tasks will be complete, and then we will start to use that site. But yeah, we've been in regular contact with JCOM.
Noted. Anything else? Yeah. Yes, please.
Happen here from Bureau of Meteorology. So this is a more general question. So I see in those presentations, we are going to close some of the task teams in a year or two. What happens then? Do we propose new task teams, or we just going to have fewer and fewer task teams? Thanks.
That's a very good question. Is anybody on? Are you willing? Yeah, thanks.
Yeah, I mean, the idea is that new task teams can be proposed all the time. If you remember Erica's diagram, the task teams are actually coming out of the tags as kind of, kind of discrete activities with objectives and deliverables so that they're closed. So, so the idea is that, yeah, new task teams would come up as needed.
On that, Anne, if you may, please, thanks. On exactly that note, is it also expected that some of the task teams can be revived? Because, for example, I think the high latitude task team died a bit unexpectedly, and maybe that was not the intention. So if we have the human resources to bring that up, would that be okay?
Yeah, I mean, of course, if the task teams are active and there's a team happy and willing to do activities, of course they should exist. Yeah,
sure. Is that something we can take up during this year's meeting, or is it something we take up offline and then we say that here we are, we want a new task team? Or
yeah, no, I think it could be revived this time if there's sure. People doing that. I don't know if Erica wants to add something.
Okay. Thank you.
Yeah, the way I understood it with the task teams is that they're initiated from the science team based on the users and user requirements. And essentially, yeah, as a science team member, you can propose something or mention it to the science team. And this is sort of what makes a task team alive. But yeah.
Cool. So that means that we don't have to wait for task teams to close in order to open new ones. And then maybe, Haifeng, if you also have something in mind that you would like to start up, maybe it's a good place now to network and discuss with anybody you think is relevant.
I do have something in mind, but I have zero experience in, which is machine learning algorithms. So I've read several papers. They have this like machine learning algorithms and like super high resolution SSTs, and I think it's a very interesting research direction. But I'm just interested. I don't have any experience in that. If we can have a task team like that, I'd be love to join.
If not because I'm here, but just because it happens that there is a presentation, I'm not sure which day, on some machine learning tests on some of the Baltic products, and I feel there's more machine learning presentations. So it's a topic that definitely is becoming more and more relevant. So I think it's a good place to start a discussion and maybe set up a task team. And I think not having any experience is also okay. This is how many of the things started anyway. So yeah, good. So if anybody is interested in machine learning, AI algorithms, has anything to do with it, I think there's something on the regional products for the Mediterranean as well, if I'm not mistaken. I see some heads nodding. Maybe it is a good time and place to think something up. Thank you. Yep, see, discussions are going. Go on, Daniele.
Hello, Daniele Ciani from CNR. I had a quick question for Mingkun Liu on the task team on Cloud Mask. If you please could provide us with a few more details on the HRSST data, mainly the availability and the format, if they are in the GRIS format or not. Thank you.
Is Mingkun online? Yeah. We can try and reach her, Daniele, because we also have the question about that. Does anybody know anything about it? Has anybody heard anything? No, I don't see any heads moving. But we will reach her and yeah. All right. Nothing more is happening. So is it okay to say that that's it? Yeah? People are tired? Okay. Yeah. Thanks a lot for staying awake, and see you tomorrow.